thank you. This is joint work with Shipra from Columbia, Costas from MIT, and Vahab from Google. And this work was done when Shipra and Costas were sitting in New York. I think Song's talk sets up a nice foundation for this talk. I explained many of the basics, but I'm going to repeat some of the basics anyway if you were there for this talk. So if one looks at sort of the auctions that's used in the web billions of times every day, it almost looks like classical auctions have found their way to the web. These classical auctions which were designed explicitly keeping single shot settings in mind, let's say for selling an object of art, etc., are being used for selling ad impressions which are being sold billions of times every day. You see the difference explicitly here. So in these single shot auctions, you really care about outcome of that single auction, who gets the item, who pays what, etc. But when you talk about billions of auctions, you don't really care about the outcome of any single round. It's all in fractions of cents. Nobody cares, and you care about the aggregate. And maybe one of these auctions informs the other, and so on. Does this luxury give us room to improve both revenue and welfare? Right? That's the goal of dynamic mechanism design. And there's a beautiful theory out there for dynamic mechanism design. It has many promising theorems saying you can achieve this and that, but many of these are not really practical or implementable. And sort of the goal has been, some of the recent work that Song described in this work has been to make all of these theorems more and more towards something that you can actually implement. Okay. You'll see what I mean. So first of all, why dynamic? Why, by dynamic, I mean that when you have these multiple repeated auctions, I want to link these auctions across time, which means that what the buyer does in auction 1 is going to have consequences on what he's going to receive in auction 2 and 3 and so on, right? So why to even link them across time? What's wrong in just running single shot auctions over and over again? Well, the simple answer is that you can improve both sellers' revenue and welfare. So there is a Pareto improvement, and kind of anything short of it is dumb, right? You can actually generate arbitrarily more revenue than single shot auctions by doing this kind of a thing. And the motivation actually is that as targeting technologies are getting better and better, display out auctions are becoming super thin. Okay, so very few buyers are participating in any single auction. That means that competition cannot be used to drive up revenue anymore. Therefore, you have to look for other means to drive up revenue. And so maybe linking auctions across time does this. Right? So here's the model. Very simple model. I'm going to describe it for one buyer. You can extend it for n buyers. So it's a t period auction. The same auction is getting repeated for t times, and where capital T, should think of it as a really big number in billions, let's say, and little t is the time index. An item arrives. Like Song said, this item is a vector of features like location, age, time, etc., gender of the user, and the buyer is able to inspect the item and decide what is its value for the item after inspection, and this value is independently drawn in every round from distribution F. This independence is justified because one visitor to New York Times and the next visitor to New York Times are not at all related. There's a kind of independence, so it is justified. Why are they identical? Well, you can look at like similar subsets of queries, similar vector of features. But anyway, you can make it non-identical later if you want. For this talk, it's going to be identical and independent distributions across time. Single buyer, as I said, it's motivated by these thin auctions. You can make it n buyers later on. And the buyer submits after inspecting this item and deciding what is its value. He's submitting a bid, and then the allocation and payment have to be decided immediately. Right? So what are the incentives for the buyer? He cares about the utility that he immediately gets based on the allocation right now, and the expected utility that he can make in all future rounds. Right? He cares about the total thing. And you have linked decisions across time, because although the values are independent across time, now you've linked the decisions for the buyers across time. That's what is dynamic here. So what's bad about dynamic auctions, right? What's really bad is that now that you have made this all linked across time, you have made it very hard for the buyer to understand even what's going on, or to reason about what's going on. And if it is difficult for the buyers, they're going to do something arbitrary. It's also going to make sellers' life difficult to optimize given this kind of behavior from the buyers. There's also a lack of buyer trust, because if you say things like, if you submit such and such a bid in auction number 20, you will receive the payoff for this in auction number 253. There's absolutely no way for the buyer to verify this kind of a thing. Okay, even in single shot auctions, it's very hard to verify truthfulness, and if you do things like this in repeated auctions, it's super hard. And in fact, even in very simple things, like suppose the buyer wants to establish the following. The seller is using yesterday's bids of mine to set reserve prices for today, right? The auction otherwise is simple. He cannot change the auction, second price auction, but the seller is using yesterday's bids to set today's reserve prices. Can you figure this out? Can the buyer establish this? This itself is a super hard problem, and there are so many difficulties here. Setting up A/B tests is super hard, and that's the topic of another paper we had in WWW with Sebastian, Andres, and Sergey from Google. So all this is to say that making auctions dynamic has its costs. Buyers are going to lose their trust in the auction. They're not able to verify what's going on. So if the buyer is not able to trust the auction, how will they sort of express this? What's going to happen? Well, they can do several things. One is that they can completely distrust the seller, which means this notion of mechanism being a contract written by the seller and given to you. You read this contract and understand and decide how to best respond is gone. I don't care about what you say about the mechanism because I don't trust you. I only trust what I hear as feedback from the mechanism by interacting with it. So I could just be a purely no regret learning buyer. I've interacted with the mechanism, I've figured out how different bidding strategies are performed, and then based on it I'll choose the best bidding strategy, right? So incentive compatibility is completely out of the window. You can't say that this mechanism motivates you to do this and that. Nothing motivates him except for real feedback. That's one possibility. Or maybe the buyer is expressing his limited trust by being a limited look-ahead buyer, right? He's a K look-ahead buyer, which means he doesn't care about the consequences of his action today after 1,000 rounds, even though you say such things in the mechanism and promise such things. Maybe he cares about the consequence only in the next one round. That's a one look-ahead buyer. Zero look-ahead is myopic, that's the extreme. Infinite look-ahead is basically the dynamic incentive compatibility, which is baked into all the dynamic mechanism design proofs. The infinite look-ahead is directly implied by dynamic incentive compatibility. And that's infinite look ahead for us, or in this case T look ahead, because T is the horizon of the whole game. Right. So given this, what should be the designer's goal, right? Ideally the designer wants to design a single auction which gets nearly optimal revenue against all kinds of buyers, right? Against a no regret buyer, against a policy regret buyer, which is a much more sophisticated version of no regret learning, which I'm not going to talk about now. You can look at the paper for the definition, or a K look ahead buyer for every value of K simultaneously, as if you designed a mechanism tailored for that specific buyer, right? You want to get close to that. Why? Well, why is obvious, because it's not possible to design separate mechanisms for different kinds of buyers. You don't even know who is who. Okay, so what best can we get, right? What can you hope for, even if you were to design specifically for a buyer? Against a myopic buyer, you can't get more than Meyerson's revenue, which is a single shot optimal revenue. And against an infinite look ahead buyer, obviously you can't extract more than the surplus itself, which is the mean mu of the distribution. Against a no regret learner, right, which is the buyer I said who completely disregards the definition of the mechanism you told him, and then he's just learning by doing different bidding strategies and figuring out which is faring well, which is faring poorly. Against that kind of a buyer, there are some no regret learning algorithms which against which you can't get anything more than Meyerson's revenue. Okay, so this is a paper you'll hear about on Thursday by Mark Braverman, Jiming Mao, Schneider, and Matt Weinberg, and this is one of the award-winning papers in EC. The other extreme is policy regret learner, which is a much more sophisticated version of learning guys. And what can you get against them? That was unknown before this paper, right? So these are the extremes. Like against the scale look ahead guys, the two extremes are Meyerson's revenue and the full surplus. Against the learners, the two extremes are Meyerson's revenue and something else. Well, something else happens to be the whole mean of the distribution. Actually, you can get the whole mean against these guys, which is what we show now. So this is our main result. We develop a single auction which will simultaneously get the following. Okay, epsilon is any number in 0, 1. Okay, although epsilon makes it look small, you can actually make it anywhere between 0 and 1. So you can get simultaneously 1 minus epsilon fraction of the surplus against a K look ahead buyer for every K greater than 1. Okay, so even if this guy is just a 1 look ahead buyer, cares about the consequences of today's actions just for tomorrow, that is enough already to extract the whole surplus if you so want it. And simultaneously you can get epsilon over 2 fraction of Meyerson's revenue against a myopic buyer, which again, like I said, myopic buyer, Meyerson's revenue is the benchmark. So epsilon over 2 times the optimal possible benchmark. 1 minus epsilon times the optimal possible benchmark, each of these. And likewise, for a policy regret learner, you get 1 minus epsilon fraction of mu, and no regret learner epsilon over 2 fraction of Meyerson, right? For instance, if you set epsilon equals 2/3, you will simultaneously get a 1/3 approximation against each kind of buyer. The interesting part is the lower bound, the matching, almost matching lower bound, where we say that any mechanism which manages to get a 1 minus epsilon fraction of the surplus against a k look ahead buyer cannot get more than 2 epsilon times Meyerson revenue. So this is interesting because anytime you get almost the entire surplus from a mechanism, you start doubting the model that if you extract the whole surplus, that's a poor model. And this kind of says what will be happening in such models, right? That any mechanism which extracts the full surplus is bound to spectacularly fail against a myopic buyer getting that revenue. And as you can see here, we get epsilon over 2, and the lower bound is 2 epsilon. It's kind of close, right? Okay. Here's the proof idea for the impossibility result. The spirit of the proof can be communicated in one slide, so I'll do it. So the revenue from infinite look ahead buyer, let's say you manage to extract the whole surplus, you're getting 1 minus epsilon times mu, which means the infinite look ahead buyer, you're only leaving epsilon times mu utility on the table for this guy. Suppose for the myopic buyer, the very same mechanism yields a utility more than epsilon mu, then that guy, the infinite look ahead guy, will pretend as a myopic buyer, which means you are bound not to yield more than epsilon mu to the myopic buyer in utility. The key point in the proof is that if you give low utility to a myopic buyer, for many distributions, this also immediately implies low revenue that you can extract from a myopic buyer. That is, revenue and utility are not like a zero, it's not like the seller and buyer are playing a zero-sum game here, where if the seller extracts a very high revenue, necessarily the buyer is getting hurt. Many times the seller and buyer's interests are tied together, right? If the seller gets more revenue, the buyer also gets more utility in the myopic case, and that drives the proof. So for intuition, here's a simple example. Uniform 0-1 distribution, half is the optimal price, get a revenue of a quarter, buyer makes 1/8, everybody is happy. But if you try to be super greedy and try to give very small utility to buyer by putting a very high price, the seller also suffers, buyer also suffers. Okay. If you're interested in the specific distribution we use, it's something like the equal revenue distribution, but for alpha greater than 2, which gives the actual lower bound which I presented in the previous slide. Okay, so now for the upper bound, the positive result. So here are some thoughts, right? Like the naivest possible mechanism is you bundle everything and then sell it at a price of t times mu for all the future rounds. Well, this is silly because first of all, this is impossible to implement. But even if you manage to implement it, all k look ahead buyers for every k less than t are going to reject this, and you get 0 revenue against them. So you look at this and then say, if the problem is with small look ahead buyers and myopic buyers, maybe the way to fix it is, okay, with probability half, I'll just run Meyerson's mechanism each round. At the beginning of the day, I'll figure out for all the billion rounds, if the coin turns out to be head, I'll run Meyerson's. Otherwise, I'll charge them t times mu, which is just bundle everything. This is also like, it has so many problems because, for a k look ahead buyer, right, for every k from 1 to t minus 1, they will not accept the bundle because it's costlier than what they can pay. They don't expect the mechanism to last for so many rounds. That's not in their visibility. So they'll just be succeeding in the Meyerson's, with the other half probability, which means all those fellows will just get, will yield a revenue of Meyerson's revenue as opposed to mu, whereas our result says that starting from 1 look ahead, everybody you can extract the whole surplus. The same with learners, right? If you offer this whole thing at a bundle, there is nothing to learn here. At the beginning of the round, you've already said what to do. So they don't know how to respond to this again because they don't believe what you say. And even apart from all these things, with the very high, this mechanism gets, like with the probability half, it gets a 0 revenue. And it would be nice to get high probability results. In single shot mechanisms, expected revenue is okay, but in repeated mechanisms, when you're talking about billions of rounds, you really want to get high probability results, not an expectation. You can try to fix this by saying, okay, I won't bundle everything in the future, I'll just sell tomorrow's round item today at a price of mu, right, in expectation. This also, many of the problems persist. Basically, any advanced selling mechanism is going to have problems, and which is nice because that's what we want to prevent. We want the buyer to be able to inspect the item and then make a payment, not just selling in advance, because he wants to inspect the vector of features of the query and then decide what to do. These all violate ex post IR. But the question is, can you satisfy ex post IR at all if you want to get results like what we said? Almost no. So this is what we show. that if you want to get per round ex post IR mechanisms with the kinds of guarantees we showed, then basically for a k look ahead buyer, you can't get more than t times log mu, okay, log k mu. Whereas we wanted to get something like t times mu, right? On the average, we wanted to get t times mu. Average wanted to get mu. So there is a log mu versus mu, an exponential separation between IIR and ex post IR. But you could ask, this still rules out t look ahead because t times log of t mu is good enough. And that's basically what we show, that our mechanism actually achieves per round ex post IR against t look ahead guys. Okay. So for very high look aheads, this still doesn't rule out good revenue, and in fact we can show per round ex post IR for those guys. So this result is tight in many ways. One way of tightness is what I showed before, the upper and lower bounds match. The other is ex post IR, where you can get, where you cannot get. You know, in the only region where you can get ex post IR, our result gets ex post IR, per round ex post IR. So here is a mechanism. It's a 5 tuple. I'll explain what each of these means. So the state space is a state-based mechanism. I'm going to continuously update states, and at each state I have an allocation and payment function. And the state is a tuple, a couple of numbers. One is the average bid that you have made in the past, and the other is the number of rounds for which you are counting the average bids over. For the past n rounds, B bar is the average bid. And I'm going to call good and bad states depending on whether the buyer has behaved well or not, right? If the buyer has been bidding on an average very close to his mean, which I know because I know the distribution, then I call it a good state. Otherwise, I call it a bad state and denote it by bot. And the starting state is going to be exactly the boundary line state, which is 1 minus epsilon times mu. And the allocation is, if you are in a good state, I am always going to give the item. It doesn't matter what you bid, even if you bid 0, you get the item. But if you are in a bad state, then you have to bid at least P star, which is the monopoly price. And even then, I'm going to spin the coin with a very small probability row and return of heads, only then I'll give you the item. So that's the punishment for entering the bad state, so it motivates you to do this well. It's kind of like equivalent to the throttling, which already happens anyway in these kinds of auctions. And so row, allocating probability row is throttling. And the payment is a simple first price mechanism. You pay what you bid, and the state transition is if the item is not allocated to you, then the state doesn't change. If it is allocated, then you update the average, which is what's happening. And if you, with a small probability, if you enter a bad state, I'll push you to a good state because I want to redeem you. So you come to the boundary state. So you can basically, so what drives the result is a myopic guy quickly will enter a bad state because he's not going to be motivated by the punishments that you're going to tell him. So he will immediately enter bad state. He doesn't care about the punishments because he thinks the game is ending right now. And once he enters a bad state, he is going to give you milestones revenue because you're posting the monopoly price in the bad state. And therefore he's going to give you rho times milestone revenue. Roughly rho times rho plus 1. And the important point is for the 1 plus look ahead buyers, even a 1 look ahead buyer is enough to ensure that this punishment that we give motivates them to never enter a bad state. And when they don't enter a bad state, then you make a revenue of 1 minus epsilon times mu immediately by definition. Okay. And likewise, you can argue with no regret and policy regret buyers, which can't get into now. So this is sort of the summary that you can simultaneously get 1 minus epsilon and epsilon against myopic and infinite look ahead. And in particular, if you choose some values of epsilon, you can get a constant factor against each of these guys. And there is a matching lower bound saying that if you get one against, if you extract the surplus against infinite look ahead, you are bound to fail very badly against myopics. Sort of the obvious future directions are extending to n buyers, which we are working on, and what if you don't know the distribution, like Song said in the previous talk. But also more generally, if you've been following this kind of thing, display ads industry has been shifting to first price auctions, right? All exchanges are doing this. So this opens many interesting questions. For instance, in most of the biggest revenue driver in second price auctions is reserve pricing. In first price auctions, reserve pricing doesn't yield immediate revenue. So how do you do this kind of thing? I expect this to open many interesting directions, and this is the first step here. We use a first price auction for partly motivated by this kind of shift in the industry to first price auctions. Thanks.
Time for one question. Can you allow for, instead of look ahead buyer, different discount factors?
What is different discount factors?
So it might, I mean, like, the discount factor is 0, the virus might happen. If it's 1, the virus.
Okay, I expect that to go through. We didn't work that out specifically, but I expect that to go through. That's the spirit.
Oh, thanks again.